Okay, so let's start discussion around a three-phase fully controlled bridge. Right, so we have talked about in a way three-phase three-pulse circuit. So this is going to be a three-phase six-pulse circuit. So you'll have six pulses in the output DC voltage waveform. Uh, all right, let's see. So let me draw the this is your load. Let's assume continuous current for now. Although in some of these circuits we are assuming continuous current, but that does not imply that they only operate with continuous current. The difference would be if the current is not continuous, the output voltage waveforms may not necessarily be the same, and therefore you may have to manually calculate the output voltage waveform and do not use the direct formulas, right? But if it is continuous current load, then yeah, then it's the formula that we derived for the previous circuit, or what we are going to do for this circuit, would more or less hold good. So now here you have three phase sources connected in star and then connecting to the bridge. So let's say this is VAN, VBN, VCN. Okay, so yeah, these are the three-phase AC sources, and these are the corresponding thyristors. So let me name them as TA1. So generally, in books, if you see, there are two approaches which are followed. Either we can write them as TA1, TA2, TA, and so on, or sometimes books would use this nomenclature, which is T1, T2, T3, T4, T5, and T6. So I would also show you what is the relevance of using this nomenclature for thyristors. So let's start drawing the waveforms that would make it a little bit clear as to why people name it with the strange way instead of going straight forward 1, 2, 3, 4, 5, 6. So let us first draw the voltage waveform. Which is the most difficult part of this video, right? Drawing the voltage waveform, but I think once we draw it, then rest everything is very straightforward. All right, so this is VAN, this is VBN, and this is VCN. Phase sequences ABC. These are the input voltages, right? So on the bottom also, let me show, this is VAN, this is VCN, and this is VBN. So this is theta equal to 0, right? And this is theta equal to 2 pi or 360 degrees. Now let us see where naturally, if all the six would have been diodes, where would they naturally start conducting? Where will T1 conduct? On the top part, when the VN voltage is highest among the three. This is the instant at 30 degrees, theta equal to 30 degrees is the point where naturally T1 should start conducting, right? And therefore we define the angle for turning on T1 with respect to this point, and let's say this is the angle at which we fire T1, and this difference is alpha, right? So here also, similar to the three-phase 3-pulse circuit, we define alpha with respect to the angle 30 degrees and not with respect to the angle 0 degrees when we talk about the phase voltage VAN. And that is because the natural conduction would start at 30 degrees. So we define alpha starting from 30 degrees. So the difference between these two things as shown in the figure is nothing but alpha. All right. Now, when would the next thing, when would T3 start conducting? T3 would start conduct when VBN is higher. So that means this point. So again, we would define alpha with respect to here. So we say this is T3. What about T5? T5 would naturally start here. So we have defined alpha. So this is T5, right? What about T2? So T2, if you see, is connected with phase C. So whenever the phase C voltage is most negative, then it will start conducting naturally. So T2 would naturally start conducting here at theta equal to 30, 60, 90 degrees, right? And therefore we can define T2 angle, which we would give at alpha plus 90 degree, right? What about T4? Now T4 is connected to phase A. So whenever phase A becomes most negative, after that, alpha after that is what is T4. And what about T6? It's connected to phase B. So whenever phase B becomes most negative at an angle alpha after that, T6. Right, so now one few things to observe here. Once we have drawn these firing angles, one other thing to observe is we fire a certain thyristor after every 60 degrees, right? So you see between T1 to T2, the difference is 60 degrees, between T2 to T3, 60 degrees, T3, T4, 60 degrees, and so on. So the observations are, the first observation as we made was alpha is defined with respect to the point at which VAC or VCA is equal to 0. That means with respect to theta equal to 30 degrees as per this figure. This is first observation. The second observation is that the firing difference between thyristors is 60 degrees. So after 60 degree, another thyristor gets fired. And third is, now you know why people would name it this random fashion, because this just makes it simple. T1 gets fired at alpha, T2 gets fired at alpha plus 60, T3 gets fired plus alpha plus 2 times 60, T4 gets fired at alpha plus 3 times 60, and so on. And that is the reason sometimes in the figure, in book, in literature, in papers, and so on, you would find T1, T2 arrangement named it like this. Okay, so far so good. Now once we have established the angle at which these thyristors would be fired, let us try to see how would the output voltage waveform look like if it is a continuous current, right? So for continuous current, let us see how the output voltage waveform would look like. Now there are two things. What is the output voltage waveform? If you see the output voltage waveform, it is nothing but the difference between the plus terminal voltage with respect to the neutral minus the minus terminal voltage with respect to the neutral. So what is plus with respect to the neutral? Is essentially the potential at plus point with respect to neutral, right? And the minus point with respect to the neutral. So if you take the difference of two, the neutral potential will cancel out, and what you get is the output voltage. So in this waveform, we'll try to draw each of them just for visualization. So what is V plus of N? V plus of N is nothing but, depending on which thyristor conducts, it could be either VN, VBN, or VCN. So if T1 is conducting, it is VN. If T3 is conducting, it is VBN. If T5 is conducting, it is VCN. And therefore, if I start drawing from T1 instant, I can say that this is going to be my V plus N, right? The top envelope corresponding to the trigger points. And what about V minus N? Now, which one has the least? When T2 gets triggered, it will take V minus Cn, right? So if we start from T2, it takes this waveform, then it takes VA, and then it takes VB. Right? So this is the V of minus N. And the difference of the two is nothing but the voltage that appears across the output voltage. So you can imagine the output voltage will have now 6 pulses, 3 because of the top and 3 because of the bottom voltage. Alright, so far so good. Now let us further move and let us try to find the average output voltage expression. Right now in this case, as you understand, everything is symmetric over 30 degrees, you can find average over 30 degrees, or you can find average over everything is symmetric with respect to 60 degrees, you can find average over 60 degree, or you can find average over 120 degree, or even for full 2 pi, right, 360 degrees. So I would not solve it the way I solved it in the previous video. If you want to take a hint, you can go to video 10.4 where I have done this calculation for a 3-phase rectifier, three pulse rectifier. In this case, I would not solve it, but I would recommend you to go back and solve it. Let me directly give you the answer which you will get, which is 3 Vm line to line upon pi into cos of angle, right? Okay, now so that's it about this 3-phase fully controlled bridge rectifier scenario, right? Here also you can see, for example, what is the maximum value of alpha that you can keep, the way we did for previous case. So let's say if you start from these from alpha equal to 0, then you can keep alpha 30. You can keep alpha as long as Vn is positive, right? So Vn is positive till this point, right? So you can keep it that way. So 30, 60, 90 and 120. So you can actually keep till it is positive with respect to phase C, in fact. So VA is positive with respect to phase C till this point, right? Till this point, if you trigger VA, previously conducting would be VC, and therefore it would take over VC. So here also, similar to the previous one, you can keep alpha going from 0 to pi, right? And that implies that again this the voltage, average voltage could be negative, and this could very well be used as a inverter as well as a rectifier. So it can allow power to flow in both directions, and that is the reason this circuit was, and in fact still is, very popularly used in high voltage DC applications on both sides of the terminal, on the rectifier side as well as on the inverter side.